Okay, so now we're going to do an electron configuration that's going to incorporate the F zone also. Remember what I told you in the last video? When you get to the D zone, you go period number -1, and you get to the F zone, you go period number -2. Okay, so we're going to do an electron configuration. And all this honestly is review for you guys. You should have had it in intro chem, whether it was Chem 1050 or 10th grade chemistry or whatever. But anyway, I'm just reviewing to make sure everyone's on the same page. Let's say we wanted to do the electron configuration of lead, right over here, Pb, okay? So we follow the same system we just did in the previous video. 1s2. So I'm going to write it as I'm going through the periodic table. Maybe I should just put this. Can you guys even see it? You probably can't really see it from so far away. Okay, you have this with you, right? We're going to go through the periodic table just like we did. 1s2, 2s2, 2p6, 3s2, 3p6. Keep on going. So we're doing lead. 1s2, 2s2, 2p6, 3s2, I don't know why my 3 is so short, 3p6, and then after 3p6, I go over here, 4s2, 3d10, remember period number -1 in the D zone, 4s2, 3d10, 4p6, 4s2, 3d10, 4p6. Now this is all supposed to be all on one line, but obviously I don't have enough room. So I'm going to keep going. So after 4p6, we go over here to the fifth period, 5s2, 4d10, 5p6, right? 5p6. So after 4p6 comes 5s2, 4d10, 5p6. Okay, so I'm done with the fifth, 5p6. Now I'm over here at 6. 6s2. Now here's where it gets a little tricky. After the 6s2, there's lanthanum in the D zone, but then we have to go down here and pick up this whole F zone, the lanthanide series. So what I will usually do is I'll go after 6s2, I'll pick up these guys because they're the inner transition, the lanthanide series, and then come back up and pick up the Ds. So remember, I said that when you get into the F zone, you go period number -2, because remember, all of these fit in right after lanthanum, which is number 57, then goes 58. So I'm going to write 6s2, and then I'm going to write 4f14, because I'm picking all these guys up, and then I'm coming back up and getting the D zone that is off of period 6. So that's 6 minus 1, which would be 5. So that would be 5d10. Remember, the reason we did 4f is that when we're in the F zone, you go period number -2. When you're in the D zone, you go period number -1. So right now we're at 5d, which is off of the 6th period. So we're right here at mercury. We want to end with lead, and so this would be 6p1, 2, 2. So 6p2, 6p2, and you're done. What you should notice and realize is that everybody in the same group ends exactly the same way. So everyone in group 4A ends with P2. Everybody in 3A ends with P1. Everybody in 7A, all the halogens, they all end with P5. 1A all have S1, okay? So anybody in the same group ends exactly, their electron configuration always ends the same way. Okay, good. Now, what is the noble gas shorthand? Instead of writing all of this, what you are allowed to do is go to the noble gas in the period before the element that you're trying to write the electron configuration of. So if what we were aiming for was lead, we go to the period before, and xenon is the noble gas. And if we just write xenon in those brackets, that accounts for the first 54 electrons that xenon and lead share. Okay, so we don't have to write 1s2, 2s2, 2p6, 3s2, all of this, blah, 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 blah. We start right after xenon with 6s2. Sometimes they'll put like the 54 here just to say that, okay, I've already accounted for 54 electrons. And then after that, you write 6s2, 4f14, 5d10, 6p2. A lot easier to do this than to do all of this. Now, sometimes you're going to see that the electron configurations are flipped around a bit, and they put the outermost shell on the outside. So basically, they'll do this. And they'll write 4f14, even though that's not the way it built up, but they do this. Anybody know why they do this? Well, 6s2, 6p2, these are the valence electrons. So when they do that, they pretty much emphasize the valence electrons and remind everybody that these are the reactive electrons. These are the electrons that are going to be doing all the chemistry. It's always the valence electrons. And why are these the valence electrons? Because they're the ones in the outermost shell. They're in the shell that has the biggest number. Okay. 6s2, 6p2, they're in the 6th shell. These are in the 5th shell. These are in the 4th shell. So it's always the outermost electrons. Those are the ones that are called the valence electrons. And when we do electron dot diagrams, we just use the valence electrons in the electron dot diagrams, which are the electrons in the outermost shell. Okay? All right, now, what is an orbital diagram? So we're done with electron configurations. Let's move on to orbital diagrams. Let's start with a really simple one. Let's say I wanted to do an orbital diagram of nitrogen, a really easy one. So nitrogen's electron configuration is 1s2, 2s2, 2p3. Okay, 1s2, 2s2, 2p3, and you stop right here. Okay, right there. Okay, so then what would the orbital diagram be? Well, I've just put one line for the 1s and put electron up, electron down, and then one line for the 2s, electron up, electron down, and then for the p, you'll always have 3 orbitals in the p. Remember how we said s has 1 orbital, p has 3 orbitals, d has 5 orbitals, and f has 7 orbitals. So you're going to put all 3 orbitals there. And where do I put the 3 electrons? Remember Hund's rule that says single, single, single before you double up? So you put the 3 single, single, single. So it's like plus 1/2, plus 1/2, plus 1/2. Okay, and when the second electron goes in, that would be the minus 1/2, minus 1/2, minus 1/2 when it comes to quantum numbers. Okay, so if you had a more complicated one, it's the same idea. Okay, you just have to make sure that you do single before you double up. Well, let's say you wanted to do the the orbital diagram for, let's say we want to do sulfur. So sulfur would be 1s2, 2s2, 2p6, 3s2, 3p4. Both sulfur, oxygen, selenium, they all end in P4. All right, so you could also do the noble gas, make your life easier, but let's go ahead and do this since I went ahead and want good practice. And then this 2s is like this, up and down, and then 2p, want 3 of them. This is all 2p, single, 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 double, 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 and then 3s, up, down, and then what do I do for the 3p? I put 3 of them. This is 3p. Where did the 4 go? single, 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 and then one of them doubles up, okay? Now, typical test type questions, I'll say, how many unpaired electrons are there in the orbital diagram of sulfur? Unpaired, this is unpaired, and this is unpaired. So there are 2 unpaired electrons, okay? If you look at, let's say, anything in group 2A, they won't have any unpaired electrons. Everything's going to be paired, 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 paired. If you look at everything in group 2B or group 12, zinc, cadmium, silver, they're all, none of them are unpaired. No unpaired electrons, okay? The noble gases, no unpaired electrons. Okay, good. So now what we can do is begin to talk about exceptions to the Aufbau principle. All right. Because building up is the way to go, except in a couple of situations. Let's say I wanted to do the orbital diagram of, electron configuration and orbital diagram of manganese. So everything in group 7B. No, sorry, forget that. Ignore what I just said. Chromium. Everything in group 6B. So everything in group 6B and everything in group 1B. So this, in the systematic numbering system, this is group 11. And this one is group 6. So these are going to be the exceptions to Aufbau. All right. And what I'll do is go ahead and do the electron configuration of, let's just do chromium. All right. Here's chromium. So chromium is, let's do the noble gas. Chromium would be argon, right? Argon. And how many electrons are argon? Argon is 18. Okay, put 18 here. And then we go 4s2 and then 3d4. Okay, so that's according to Aufbau. Now, if I was going to do the orbital diagram, it would be argon. Here's my 4s. And then 3d4, 1, 2, 3, 4, 5. This is 3d. Single, 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 single. Right? According to Aufbau, this is what it would be. But I just got through telling you that this whole group, exception to Aufbau. Why is there an exception in this group? Because orbitals are more stable, or electrons are more stable, or atoms are more stable. Think of it that way. If they have completely filled subshell or half filled. What does that mean? I mean, it means that chromium would be happier if there was a half-filled orbitals. They're all half-filled. Like if I had an electron here, chromium would be better off, would be more stable. Is there any way I could get an electron here? Well, if I take this s electron and I promote it and bring it over here, this is not the excited state. This is still the ground stable state. We're saying this makes it even more stable. If I take this and bring it over here, now look, I've got half filled, half filled. So the key is to go to half filled or completely filled. You can't just promote randomly and promote a whole bunch of electrons. You can promote one electron from an S to a D. That's what you can do. So instead of chromium being 4s2, 3d4, because we said it's an exception to Aufbau, It's actually 4s1 3d5 with an argon over here. See? Okay, in the next video, I'll do a couple more examples, and hopefully all this will sink in reasonably well. All right.